Okay, so what I'd like to do today, because it's my last course, last lesson today. So what I'd like to do is to give some illustration related to application or more applied application of what we learned before. Okay, so we will go actually over a concept that we already learned about, but in concrete situation, in real situation, we'll talk about scattering, about speckle, about mean-free path, all that, but in context, okay? And I think the best illustration is to talk about what has been done related to imaging. So imaging in general is not just taking pictures. I mean, you have an object that you want to image, but there is a medium in between, and usually you have a scattering or absorbing medium, and that makes the imaging complicated. Okay, you want also to reach small sizes, so you want resolution. You want not only a picture, you want a three-dimensional picture, so that's called tomography. You want to have a map, a full map of the object. So all these are issues that are related obviously to light scattering when you want to image with light. And light is useful. Why? Because the wavelength of light is very small, so we can expect to achieve very high resolution. Okay, typically on the size of the wavelength. So that's the topic here that I will address first. We try to cover that, and if we have time, I will talk about random lasing, maybe in the third part of the class. We'll see. Okay. So don't hesitate to stop me or to ask questions. It's just very open, like every time, but this one is easier. Okay, so imagine. So you remember this picture by George de la Tour, this painting, very realistic in terms of light effect, light scattering. If you zoom on the hand of the young girl here, you see beautifully how the painter showed the scattering through the skin, through the hand. Okay, and you can do yourself the experiment, and you see typically the same, this type of image. Okay, so what you see clearly, first you see that we have red light coming through the hand. Okay, if you hide this part, the only thing that really cross the tissues is red. You see that depending on the thickness, okay, when you are on the edges or when you have bones, okay, then it's getting darker and darker. So you know all this concept is related to mean-free path, okay, how much you can penetrate the medium, okay. What else we can say? Yes, the image is diffuse. Okay, we don't have any information. We don't image the inside of the body here of the hand. Okay, so there is really a blurred information of light scattering through. We don't see the bones like you would see with X-ray imaging, for instance. Okay, so why do we have this type of picture? So you have this famous representation here of the absorption and scattering coefficient. Essentially, this absorption coefficient here as a function of wavelength. So in the body you have different type of element. Mostly you have water. So water molecules, H2O. You have hemoglobin. The skin gives you also melanin. All those components, there are many more, but those components are they have a spectrum of absorption. Okay, that's what is represented here, and also they, depending on the side, they may scatter. So essentially here we are talking about absorption. So what you see for the water, you see you see some absorption here in the ultraviolet and violet section of the spectrum, and then it starts again here on this side, okay, where you have very strong absorption for the far infrared. And there is a window here where the water does not absorb, okay, but on the other hand, the hemoglobin has peaks here in this region here where the absorption is very strong, and the melanin has decaying absorption coefficient with wavelength. So when you look at that, you see that the only window where we can expect to see something is where you have not too much absorption from water, from hemoglobin, and from melanin. So this really in this very small window here, okay, and this is actually at the limit of the infrared, okay. So that's what you see here, red coming through the skin. But where you have actually a minimum here of absorption for these different elements here, the scattering becomes dominant, okay. So why? Because the wavelength is on the length scale of different elements in the body, the cells, different cells and all that. So all this is strongly scattering. So what we have transmission, no absorption, but mostly diffusion of light because of multiple scattering. Okay. So this is called the what did I write here? So near infrared light is optimal for deep tissue optical probing. So this is called the therapeutic window. That's the window where we can expect to have some imaging approach here. Okay. So remember what we have learned earlier about scattering. I tried to do something with ChatGPT. It's not very good, but okay. So you have a source, you have a scattering medium, okay, and you have photons crossing the medium. Okay, it takes more or less time. Few photons will go ballistically directly to the detector. Okay, so that's the first photon to arrive. So if you look here at the time of flight distribution, you see that the first is the ballistic photon to arrive first on the detector. Then you have what are called the snake photon, so the photon that goes like that, okay, like a snake with few scattering events. Okay, so they come later. And then you have multiple scattering through the medium, and which is the detector much later. Okay, so that's the diffusive part with a long exponential tail here, which is characteristic of the diffusion, and the longer and longer trajectories experienced by light through the scattering medium. Okay. So what can you use to image? So the first approach is to say, let's try to catch the few photons, ballistic photons. Okay, those ones we know. I mean, they will perfectly image. I mean, reflect or go through the medium without distortion. So we can image clearly with those photons here. There are very few crossing the system. Okay, but maybe there will be techniques or at least scales on which we can detect them. So that's the first approach, measuring the ballistic photons. So let's see how we can do that. So there are different techniques. I'm just citing a few of them here. Time-gated ballistic photon imaging. Okay, so the idea is just to select in time domain. Okay, the very first photon. So if I go back to this picture here, time gating. That means that I just open my camera only for this time length here, avoiding all the other components. Okay, and I will have an image of only the ballistic photons. This time gated ballistic photon imaging. Okay. Confocal microscopy. I will show you in a movie just after that what type of technique is that. Typically, yes, it's a special selection of the light which is either reflected by the object or most of the time emitted by the object. So we will see that most of the technique they use fluorescence, okay, to image actually what is inside the body. So usually you inject some chemical inside the body, and you expect to see luminescence from the inside of the body through the tissues and through the skin. Okay, so that's one approach. Another approach are nonlinear optics based on either 2 photons or 3 photons microscopy. So it's based on a nonlinear effect. I will say a few words about that. And one technique which is well known, probably you've heard about that, this is called OCT, optical coherence tomography. Okay, and you see that these different techniques, they can explore more and more deeper inside the medium. So I put here one mean-free path. Okay, so we know that the mean-free path in optics for tissues is about what? Few tens of microns. Okay, so that's the deepest you can reach, one mean-free path. Here, few mean-free paths. This one can be optimized depending on the type of object that you want to image. And OCT is probably one of the best, going down to 25 mean-free paths, okay, times 50, okay, 20, 50. So it's up to be interesting. This is strongly used, for instance, for imaging the retina, everything which is not too strongly scattering. So these techniques extend the range of imaging in tissues to up to 1 millimeter or more by rejecting out focus light and improving sensitivity. Okay, so there are some references here if you are interested. So I show you that's an animation that explains to you what is fluorescence microscopy, fluorescence imaging. Okay, and based on that, what we call confocal microscopy. Tell me if it goes too fast. I will stop it. There is some sound. So you have magnifying lenses, dichroic mirror. The first filter selects the light. So the light comes and excites the sample here. The sample is made of fluorophore, so it's fluorescent. Okay, so it will emit back fluorescent light. Okay, that is directly imaged on the camera here, using some filter here to remove the other wavelength. So that's fluorescence microscopy. Now you can improve this technique. So this allows to detect a very small amount of molecules in biologic samples. So now you can improve this technique by using confocal microscopy. So you use a pinhole here and a pinhole there. Okay, so the light will be focused actually at some position and some height, some plane here. Okay. And again, you measure the fluorescence of this small area here, and you image it. And then what you can do is to scan the sample, different position, okay, and you can reconstruct the image, the full image, not only in 2D but only in 3D. Okay, you can also, by changing the position, you can actually go deeper inside the sample. And you can obtain a 3-dimensional image of the sample itself. By doing layers by layers, you can okay, so you can get good spatial resolution here. And also you can do what is called tomography. That means you can map in 3D the object. Okay.
Very cool.
That was, yeah. Okay, so just a review of the different. So this is the confocal here. So those are some examples here where we can see the type of images that you can achieve. So these cortex. that I don't know which piece of meat is that. I have no idea. So this is OCT, and this is two-photon microscopy. So two-photon microscopy, you know that when you just pump a system at a higher wavelength than its emission, its fluorescence, okay, then you have to use quite high energy light, okay, and typically this will be strongly scattered. But you can do two photons. That means that you pump by nonlinearity. You can sum actually two photons with the same wavelength to reach the upper state of the fluorophore, or you can use also three photons. Okay, and by that you can actually change the wavelength of the excitation, and you can reach. Remember this window, this therapeutic window, where light will go through more easily than at those wavelengths. Okay, so that's the idea of using three photon microscopy, is that the pumping light will be less scattered at those wavelengths than at low wavelengths. Okay. OCT. So OCT this is actually optical coherence tomography. So it's a technique, it's an imaging technique that was produce quite high resolution images and can go quite deep inside the sample. I told you 27 min3 pass. What is the idea? Actually, the idea is to use a source which has a low coherence, okay? Which means that if you want to make interference with this source, you have the two passes should be very close one to the other, okay? Otherwise, you go beyond the coherence length of this light, and you lose the coherence. So you lose actually the interferences, okay? So by adjusting a reference and the image itself, you can probe in depth the tissues, okay? By adjusting the length of the reference with respect to the length of the signal itself, okay? So by using a very short coherent source, you can actually scan in three-dimensional your sample, and you can image quite correctly the sample. That's another example here in electro cell imaging. So I guess this is probably a neuron. I'm not sure. Okay, so you see you can do different type of imaging playing on the. So those colors actually are artificial colors, okay? But they probably correspond to different type of fluorophores. So that's typically a static imaging of different objects or different tissues or cells. There is a technique which is called functional imaging. Maybe you have heard of this expression. When you say functional imaging, that means that you image some part of the body in action. Okay, so there is a parameter which is changing. Okay, for instance, the blood circulation. Okay, and you image as the system is changing over time, or over frequency, or over position. Okay, and this change actually creates a dynamic in the imaging that gives you a much better image of the. So that was the early stage here. Okay, and things have improved since then, and now they can do very nice images of the retina. I don't go too much into detail here. I mean, the ultimate goal will be to use the ballistic light to image the full body. Okay, so that was a picture that was a picture that was shown in the early days of imaging through scattering media. Okay, so there was like some hope to be able to catch few number of ballistic photons to image the full body. Okay, but when you put numbers, so you remember that the law for ballistic photons is an exponential decay. Yes, you remember that? So we have the Beer-Lambert law. Okay, if you remember this picture, the incident light, transmitted light. So the transmission goes like exponential decay with length or the thickness of the sample divided by the mean free path. Okay. So what is the typically the mean free path if we let's say we take a large value like 50 microns, okay? So you can make the calculation here, what would be the transmission through few centimeters. So in tissues at 5 centimeters for 1 watt input, 1 ballistic photon per billion year, okay? So that's very, very small. So there is no chance to reach this type of technique here. After a centimeter or more, you don't have anything left. Okay. So just to review something we discussed many times, the scattering mean free path, the transport mean free path. That's a very nice picture, by the way, a nice illustration. So you look at light going through a scattering medium. This is like the Eiffel Tower. So you have the ballistic regime at the beginning here, and then as the scattering increases, the light is more and more diffuse, and then you reach a point where it's the random walk, you are the diffusive regime. Okay, so you remember what is the limit for the ballistic light? The ballistic light is exponentially attenuated, so that's the Beer-Lambert rule that I showed you before. What about the diffusive light? So this is defined by the transport mean free path, and the idea is that after a few transport mean free paths, photons have lost memory of their initial direction. Okay, so up to 1 mean free path here, you still see a progression in that direction, but at some point after a few mean free paths, it's a random walk, so it explores all directions without any memory of the incident light. Okay, so that's the issue. What I described until now is imaging with the ballistic light here. Okay, you can explore deeper here, but then I mean you reach distance. I mean the resolution. The resolution actually is getting worse and worse. And that's what we're going to see when you want to image using diffuse light. So if you want to go deeper, you can go deeper, but at the price of the resolution. That's the main message, okay? So deep optical imaging, typically what has been developed, the technique that has been developed is called diffuse optical tomography. So usually it's based on fluorescence imaging. Okay, so you are looking at an object which is fluorescent. Okay, you need to work in the therapeutic window, so in the near infrared. This is based on model. Okay, so people are using a theoretical model, typically the diffusion equation. Okay, that's the main model which is used to analyze the measurements. Important information that you need when you measure some medium, you need to measure the absorption coefficient and the scattering coefficient. Okay, so those are the parameters that goes directly in the diffusion equation. Okay, so that's the technique that is used. The objective, what really is the objective? For instance, you want to detect early enough cancer, okay, a tumor. So you want to see something small at the beginning, okay. So for instance, for early breast cancer detection, the idea actually is to avoid biopsy, okay, and to be able to detect as early as possible any tumor. So they have developed this type of technique. Those are actually optical fibers that image in three dimension the breast. That's another example here on small animals. So you can actually detect tumors, but you see that the size of the tumor is already big. Okay, we are talking about centimeters. Okay, so yes, we can see something using those techniques in the diffusive regime, deeper inside the tissue, but we lose resolution clearly. So time-resolved diffuse optical tomography, the idea is to recover target information using primarily multiply scattered light. They use algorithms, they use theory behind that. Typically the limit is a few centimeters. Okay, I don't go too much into the details here, it's technical. But the idea is that the price to pay, diffusive imaging, has a very low resolution, millimeter to centimeter. Okay, so you can actually summarize that different techniques here in this diagram. So this diagram shows you how deep you can go to image here. So the imaging depth as a function here of the resolution. Okay, so the resolution is in microns. Okay, so microscopy, standard microscopy, wide field microscopy is able to probe not far than few microns. Okay, but with a very good resolution. We are talking about microns. Confocal microscopy, what I mentioned to you before, multiphoton microscopy. You can go a little bit further, tens, hundreds of microns, with still a good resolution. OCT is here, somewhere in the middle, with a resolution of about a millimeter, a resolution about 10 to 100 microns. And then diffuse optical tomography here, that's what I mentioned. So this really, in the other regime where you are working on the diffusive light, so you see that you go much deeper into the tissues, inside the tissues, but the resolution is lost. You are in the centimeter or 10 of centimeters. Okay. There is an intermediate technique here that I will mention at the end of this talk, which is a new approach that can be interesting where you want to be in some intermediate regime. Actually, this technique couples acoustics and optics to image the tissues. So that's the state of the art here. You have confocal microscopy, micron, OCT, 2 to 10 microns, even 100 microns. Ultrasound, so that's the standard ultrasound techniques to do medical imaging, about 150 micron resolution. Then you have high resolution computed tomography, so this is CT, okay, you are familiar with that, CT, 200 microns, and when you go to MRI, you have a resolution of about a millimeter. So those are the best techniques actually used to image. You need help?
Wow. Staying home tonight, people.
Okay, there are other issues, okay, about imaging, and you know that MRI is very nice, but it's very uncomfortable technique. So they really want to avoid that type of imaging because it's very noisy. It's very uncomfortable. You should not move.
Yes.
At all.
I done it 4 times.
Yeah. It's very difficult with small kids. They cannot stay still, and it's very difficult. So yes, there is room to improve these techniques, and I mean I don't know if you have this perspective, but you can see over these last 30 years. I mean, how much the imaging grew actually in the medical environment. I mean, now you go to any doctor, they start to do some imaging, some CT, some ultrasound. It always starts with that. I mean, imaging now is really the first step if for any diagnostic, and so it really took a big part in the medical environment. But we are limited, so I will not go further in that part, but I will go back to speckle. Okay, so that's something that we studied. And I will tell you about how we can use speckle actually to do some imaging, to have imaging techniques. The advantage of the speckle here, a speckle pattern, okay, is probably complex, okay, but it's fully coherent, okay. All the information of the medium is there, okay. And on top of that, this is something that you can control, and I will show you how you can control that. So if you work with monochromatic light, you get actually a speckle image on one side, on the other side. If you play with several colors, you see that you get different speckle patterns depending on the wavelength, okay? And that can be interesting actually to do imaging, and I will show you how. And the technique that has been developed quite recently is called wavefront shaping. Okay, so that's what I would like to introduce now. And yeah, so let's consider first two different regimes. So you can have multiple scattering in different contexts. Okay, you can have multiple scattering on large scales with low contrast. So this is typically turbulence, like atmospheric turbulence. Okay, so that will modify the wavefront. It will perturb the wavefront. And this is very useful. This is actually the context of in astronomy when you want to do sky imaging. Okay, you need to compensate for the atmospheric perturbation. So you can either send your telescope in space, but this is very expensive. But you can use actually other techniques called adaptive optics. Okay, which is very, very efficient. Actually, you can achieve very nice resolution, very close to what you can achieve in space. So that's the case of weak scattering. Okay, large scales, low contrast. Now, if you go to short scales and high contrast, okay, so these are regimes that we studied here, strongly scattering media. Okay, so we are in regime of multiple scattering. So what can we do here? Can we do the same approach here? So that's a new technique that I will describe about wavefront shaping. So I first say a bit about this part, about adaptive optics, wavefront perturbation. So you have a wave coming on some optical object here, okay, and you want to focus. And what you discover actually is that it's very hard to focus because of this small perturbation, this weak perturbation, but that's enough actually to blur completely the focal spot. Okay, so that affects imaging here. For instance, in astronomy, you have a twin star, but this is completely blurred by atmospheric aberrations. Okay, interesting here, you have what is called the point spread function, which is actually the image at the focal point of a source. So you have a source, and you have here on the first line you have a pupil, the size, the diameter of the pupil. Okay, so actually you close or you open a pupil in front of the source. So when you have a very small aperture, so it's like the eye, okay, the pupil in the eye. Okay, when you have too much light, the pupil closes down. Okay, with a small pupil, what you observe with the perfect eye, you would observe this. With the typical eye, you observe the same type of pattern. Okay, but obviously you have diffraction because you have a small aperture, so the light is diffracted. Okay, over a quite large area. If you increase the diameter of the pupil, then you reduce the diffraction, okay, but you start to have small aberration, okay, that you see here. And as the pupil increases in size, the optimal focus will be smaller and smaller, but the actual image obtained on the eye can be strongly perturbed. Okay, this is because of all the liquids that we have in the eye. Okay, so that's a problem. So you see actually that there is an optimal regime which is in this area here where you can increase resolution, okay, but and limit the aberration. Okay, so by playing on the diaphragm, on the pupil, you can actually optimize the image. That's what the eye does by itself. Okay. So it's a trade-off between diffraction and aberration in biotic optics. So for astronomy, for space imaging, what is the principle of adaptive optics? Are you familiar with that concept? No? So the idea is the following. So you have, so you measure so light from the telescope. Let me see how to. Okay, so we have light coming from the telescope on this device here. So this device is called the Shack-Hartmann sensor. Okay, so the idea is the following: is that you have here an adaptive mirror. So that's a mirror that can be deformed. Okay, this deformation can compensate for the distortion of the wavefront due to the atmospheric perturbation. Okay, so you have here your camera where you do the imaging, okay, and you have a reference here that will sense actually the image and that will correct the wavefront, the incoming wavefront, by adapting the mirror itself to optimize the image, to clarify the image if you want. Usually what you need is a reference, so you can use a guiding star, okay. So a star, you know, it's a point in space, so you optimize the wavefront so you recover a point source, okay. Or you can use a laser, okay. That's an artificial guiding star that can be used to image to optimize the. I mean, this is a dynamic process. Okay, you need continuously to adapt the mirror to compensate for the aberration because they change all the time. Okay, and that gives you very nice results. You can see here, for instance. So when adaptive optics is off, this region appears completely blurred. Okay, when the adaptive optics are on, then you can resolve all those stars here with a very, very high resolution. You can see details that you will not see otherwise. Another example here. I don't write what is this, some kind of nebula. I don't know exactly. So you can see actually the details here. It's a galaxy, I guess. It's just a galaxy, and you can see stars inside. Okay, so that's the principle. So typically, what is used in telescope is this type of mirror, which are like several mirrors that can move, that can be orientation can be changed. Okay. So first, yes, it allows to have very, very large diameter telescope. Okay, you can have mirrors at different distance. Okay, you can increase. The more you increase the size of the mirror, the more you increase the resolution of your image. Okay. Improve lateral resolution, improve axial resolution by playing on the mirror. Okay, so that's those are examples here. You see different images here. Okay, and probably the best example is the James Webb Space Telescope, which has also a mirror made of several mirrors here, as you can see here. That's by comparison, that was the Hubble mirror. Okay, they had to change because they made a mistake in the calculations, if you remember. So you see the size is much bigger, and each element here can be monitored, can be oriented independently. So you can actually optimize the image. I think, yeah, you can look at this video if you want to take time, but you'll see how they actually optimize the orientation of the mirrors by it's a feedback loop. Okay, you want to actually bring all the images at one point. Okay, so by a feedback loop you can adjust one mirror after the other, and the result is so that's not so the result is very nice. You can see here. So that's different type of telescope. I guess Earth telescope. I'm not sure. And this is the James Webb. So this is really amazing. I mean, it's like another world. So this is really a revolution, I mean, for astronomy and imaging for this kind of system. This is a huge revolution, opening the doors to new discoveries. That's the same technique applied to the imaging of the retina. Okay, so that's without correction here, without adaptive optic correction. And when you use adaptive correction, you can see actually the, how do you call that, the cones, the cone photoreceptors here, okay, which are actually are on the surface of the retina that catch light, different colors. Okay. So all that is based on this type of technology. Okay, there is a lot of technology behind that. So you have two types of system that gives you a control on the wavefront. So you can have deformable mirrors, as I showed you before. So this is a small one. This is a small structure where each mirror is driven by a piezoelectric device that can orient differently or either orient, or it's like a in this case like pistons. Okay, so by pulling one or the other, you can change the phase. Actually, you can adjust with very high resolution the phase of each pixel here, but there are a small number of pixels like that. Okay, typically 10 to 100 actuator. Now they do much better than that. The course is quite large, 10 to 20 microns. Speed is quite slow. Sorry, the opposite. It's quite fast compared to the other one. So here is a completely different approach. This is based on liquid crystal. So it's a matrix of liquid crystal. Million of pixels, okay, and each pixel can be addressed independently, so we can change the reflectivity or the phase of each pixel, okay, and this is actually what is used in this projector here to project the image of my computer on the screen. Okay, this is typically what is used there. So that's really a revolution. This technology are really revolutionary. So that's okay for adaptive optics. Let's go now in strongly scattering media and see how we can use this technique, the same principle, to image through complex media. So focusing through a scattering media, we have some reference here. The idea starts here. The idea starts by the fact that if you shine light on the disordered system at one position, at another position, you see that the speckle changes. Okay, so the speckle depends on how you shine light on your sample. It depends, as I showed you before, it depends also on the wavelength. By changing the wavelength, you change the speckle pattern. Okay, so the speckle pattern has a lot of information, and especially it will depend on the position here. So you can imagine that if you combine smartly the way you illuminate the sample at different positions with different phases, you can combine this speckle pattern so that you may have an enhancement at some position and a reduction elsewhere. Okay, so you can actually focus light somewhere behind the scattering medium by combining smartly all those speckle patterns, okay, because there are interferences patterns, okay. So the sum of interference will give you a new interference, and that can be something interesting for imaging, at least through a scattering medium. Okay, so that's where the idea comes from. So you have a scattering medium. If you illuminate it with a plane wave, okay, you have a speckle pattern. You can imagine that you can engineer the wavefront so that you can have something different here, and this is based on the fact that the scattering is a linear transformation. Okay, so you can see the scattering medium as a matrix, transformation matrix. Okay, in that case it's a transmission matrix. You come with some incident field and you get an output field here. Okay, so it's a linear relation between input and output. Okay, so if we can shape here the wavefront, okay, we can adjust the input to get a given output. Okay, the idea is very simple. Let's say I want as an output to have intensity at the center and nothing elsewhere. Okay, so I just inverse the matrix here. Okay, and I will get what should be the input to get the desired output. That's the idea of wavefront shaping. Okay, and that can be done with these spatial light modulators based on liquid crystal, or with these controllable mirrors, and yes, then you can really shape the wavefront. So this is a picture of a wavefront that will be, you see, I mean, you introduce phase differences between each pixel, and that can be used actually to image with the scattering medium. Okay, so the idea is that by shaping here the wavefront, so this actually is given by the inverse of the transmission matrix, the linear transformation here. If this is exactly the opposite of the inverse of this matrix here, then you can get what you need at the output. So if you have like a point excitation, a point source, you'll get a point at the output there, a focal point at the output. So how can we realize that? How can we guess? How can we guess what should be here? The inverse of this matrix. So how you can guess what should be the shape? How can you shape actually? What should be the phase diagram here that will shape correctly the wavefront to obtain focusing on the other side? So there are two approaches. One approach is a blind approach. That's okay. We don't know what should be the value of the pixels here. Okay. But what I can do is that I put a detector, okay, and I say I want to maximize the light on this detector and minimize it elsewhere, okay. So to do that, okay, I have a feedback loop. I measure here. The computer will tell me, okay, I'm going to modify the wavefront here. I mean, the SLM here will modify the value of my pixels. If I get improvement on the detector, I will say continue in the same direction, and the system will iteratively optimize the wavefront in order to maximize the signal detected here. Okay, so it's a blind approach. You don't know what's going to be the result here, but at the end, actually, you get.
You can also use it for like encryption, like
encryption. You mean to code?
To code the data and to use this kind of method.
Right. Yeah. There have been some work on that, right?
Yes.
So I show you an animation of the idea of this iterative approach. Okay. That's the end of. I don't know why it doesn't start at the beginning. So starting at the beginning here, you have. So this is the SLM. Okay. Stop it. Stop it. Okay, so this is the SLM, and you play on each pixel. Okay, you adjust the phase of each pixel. Okay, so that the spot here. So it's not really well synchronized, these three pictures. So you start with the speckle pattern here, and as you modify the pixel here, you see that more and more energy will be focused at the center, and the rest of the speckle goes down. Okay, and it corresponds here. It's not really synchronized, but it corresponds actually to align all the small. Remember, all the scattered waves that interfere at the output here. You want actually to align them in phase to maximize the signal here, and they should be out of phase elsewhere to reduce the intensity as well. Okay. So this approach has been tested, okay, and it works nicely. So that was demonstrated in 2008. You start with so you have a scattering medium here. This is just paint on the glass.
For the optimization, are they using linear functions?
What do you mean linear function?
Linear. For the optimization.
The type of
like sigmoid.
Yes. So that's a full story. What should be the algorithm that you use to be efficient? Okay? Mm-hmm. So yeah, so you can use the standard one, but you can actually improve that by using. There are many optimization algorithms that have been trying to optimize that. But once you optimize, then you can shape the wavefront so that the scattering medium will be traversed by this wavefront, and we will focus on the other side, and you see the result here, the speckle pattern. And once, so it's not, you are not eliminating the speckle pattern; it's still there, but you maximize the intensity where you want, at the position you want. What I wanted to show here is the same, is the result. So the spot here is about 1,000 times the background, which is nice. So it means that you have like an opaque object, okay? The light goes through, and you can actually see you can actually focus on the other side. It's like the scattering medium becomes transparent for your light. Okay, so by playing on the source itself, on the wavefront of your source, somehow you make your scattering medium into a transparent medium, almost. Okay. So this is not yet imaging. I will talk about that. It's just focusing on the other side, but it's really quite a nice achievement. So that's the first approach. It's an iterative approach, okay, where the algorithm actually will converge to an optimized wavefront to focus on the other side. The second method is really measuring this transmission matrix, this T that I mentioned before, okay? You can measure it. Once you measure it, you can invert the matrix and find any wavefront that you need to achieve any output that you want, okay? So that's just a picture to show you that this is a simple case of a lens. For the lens, the transmission matrix is very simple, just 4 elements. But when you take a piece of sugar like that, which is strongly scattering, okay, you get a huge matrix, okay, with many elements that you need to calculate. So how do you do that? So you can imagine the following technique. You have here an SLM, so you control pixel by pixel the phase here, and you have a CCD camera where you can measure pixel by pixel the intensity of your speckle. Okay, so you turn on one pixel here,
and then
okay,
you see where
and then you scan all the pixels there. Yes. So you build one line of two matrix, then you go to the second one, etc. Okay, so here you use like a basis. You need some kind of vectorial basis that will be converted at the output, and you get this way all the parameters of your matrix. So that's a small example. So that will be the case of free space. So this is just a diagonal matrix, okay. But if the medium is scattering, you get an output that looks completely random, okay. But this is the matrix. Actually, that's one matrix that has been measured in the experiment I'm going to describe now. So that's the experiment. So they use again a spatial light modulator based on the liquid crystal, like millions of pixels here, and they use a CCD camera, and that's the sample, which is like a block of paint, which is strongly scattering, so it's a thick layer of paint. So what is important is that the medium should be linear, multiple scattering, stable, okay, over time, and should not absorb that much, otherwise we lose the information. At the input here, we use some bases, so it's a particular basis that has been used called the Adama basis. Okay, so you scan each element of the basis and you measure on the other side the result on the camera. For each pixel, okay, you get a response. So you scan here, line by line, and you obtain this typical matrix here. Okay, so this matrix, this transmission matrix, is a fingerprint of your medium. Okay, all the information of your complex medium, your scattering medium, is there. Okay, that's the magic of this matrix. So it's a signature of the random medium, useful as long as the medium is stable. Okay, obviously if the medium start to move, like in a life, in a living tissue, for instance, that will change over time. So that's the problem with this measurement. But once, if the system is stable, you can measure it. Okay. And by choosing so that's just a summary. So by choosing a suitable basis, the wavefront incident on a sample can be decomposed into orthogonal modes. Okay. The microscopic equation of the transmission matrix requires an enormous number of elements. Yeah, it's a large number of elements to describe that. In the experiment that I showed you, they use actually a 16 by 16 pixels. Okay, so quite small. But they measure amplitude and phase. Okay, so in optics, if you want to get phase, you need a reference. Okay, you need to do some interference process to get both the amplitude and phase. So we'll see how they did that. Okay. Okay, so enable the decapacity of light transport in diffusive sample. Control light propagation, you can focus, you can image. I will show you can image through the scattering medium. So that's the experiment, and you see that. So that's the wavefront actually. Okay, for a given distribution of pixels here, different phase distribution of the pixel, you get a given wavefront. Okay. That will be used to illuminate the sample and focus. So you can decide to focus here. The same matrix is used to focus at the different position or to get 3 focal points. Okay, so you can actually do whatever you want. Okay, and you can even image actually some object. So I will show you at the end. I will show you how you can object some objects, some image. Okay. But this is actually imaging behind the scattering medium. Okay, if you want to image inside the body, it's another story. Okay, how can you do that? So here you can go through a scattering medium. How can you image inside the scattering medium? We're using the same technique. So that was proposed here. Actually, if you can put inside the medium, you can put some fluorescent element. Okay, like here, you see the small dot here. So you can use the light that is re-emitted by the fluorescent object here as the target. Okay, let's say you want to focus on this position, so you want to maximize the light that is re-emitted by this object. Okay, so you detect the emitted light, and again you can do feedback. You can use a feedback loop to optimize the focus inside the sample. Okay. So this is by using a 150 nanometer fluorescent particle hidden in thick zinc oxide. Zinc oxide is white paint. Okay, so it was demonstrated that you can actually focus inside the system, but you need something there. Okay, to have a point to measure. So this was about focusing inside or on the other side of scattering medium. If you want to do imaging, just focusing is not imaging. Okay, we need to scan somehow, and a way to do that was proposed is to use the memory effect. I mentioned that I think 2 weeks ago, maybe. The idea is that one of the parameters that you can change is the angle of incidence here. By changing the angle, actually you move the speckle pattern. Okay, so if you change here, you see that the speckle pattern remains the same. There is some correlation here that keeps the same speckle pattern, but just shift it in position. Okay, so using that, actually you can scan the object and you can have an image of the object. Okay, so that was used here in this experiment where they had like a given pattern, okay, like a flower, kind of flower here. Okay, so that's the object to image. The rest actually is the reference part. So that's the beam. The beam actually illuminate the object, and this illumination is observed through a scattering medium. So you put a scattering medium in front of that. You don't see anything left. Okay, really, you don't see anything more. But they use actually the outside here of the image to have a reference for the light and to be able to. Oh, you didn't stop me, by the way. So maybe I finish with that. Yeah, just to show you some results. So that's the input mask. Okay, that's what you would see for the scattering medium. Nothing, just a speckle pattern. So they use different techniques: inversion, phase conjugation, and regularization. I don't go into details here, but they can actually achieve a very good image of the object through the system. Okay, so they have very relatively recent technique that have been developed there for that. Maybe we can make a break now. Yes, let's make a break maybe. I will go back to that as well. Okay. If you don't want, we can continue. Yeah.
I started everybody up fine.
Okay, so I just want to show you something interesting here about focusing. So I explained to you this technique of wavefront shaping to focus light beyond the scattering medium, strongly scattering medium. If you compare the focusing of a simple lens, okay, you know that the lens will focus at a given size. The size of the spot is diffraction emitted, right? And the diffraction limit is given by lambda f. F is the focal length of the lens, divided by d. D is the diameter of the lens. Okay. So the smallest spot that you can get is limited here by this formula. So if I have a very large lens with a large diameter, I will improve the focusing. Okay. But obviously I will be limited by its size. Okay. What is interesting is that if you take, let's say, a scattering medium instead of a lens, okay, and you focus through the scattering medium, what you discover is for the same size as the size of the lens, you get a spot which is much smaller. Okay, and the reason for that is that multiple scattering improves the resolution by increasing actually you see the light. What you need when you have a lens is you need light that goes through different passes, okay, to recombine on the other side. Here you have so many trajectories inside the system. It's like if you can unfold it, it will be like a very large lens that focuses light on a much smaller spot. So that's a very interesting feature of scattering media. Okay, we started with the idea that the scattering medium is really a problem to do anything with. Okay, here you discover that you can use it actually to improve the resolution of your image or of your focus here. Okay, better than the standard lens. Another point that I want to show you also, I don't want to go too much into details, but if we go back to this transmission matrix T here, okay, you can actually transform this matrix using what is called a singular value decomposition. Are you familiar with that? Have you heard of that? No, SVD, singular value decomposition. So the idea actually is to find the right vector U, the transformation vector U and V here, that transform T into a diagonal matrix. Okay, so it's like diagonalizing the matrix. Okay, but this is true even for a rectangular matrix. Okay, U and V are unitary matrix. U actually correspond to the right incident channel, and V to the right output channels. Okay, corresponding to different value along the diagonal. So if I have a diagonal here, so the first value here will give you the transmission from one channel to the other channel, that gives you the highest transmission. Then the next one, which is smaller, will give you a smaller transmission. So each of the diagonal elements correspond to going through the scattering medium, okay, following different channels, different way to sneak in through the scattering, okay, and to transmit at the output. And when, yes?
So tau is diagonal, like he uses a LU matrix?
So this is like a matrix, but only with a diagonal and zero on both sides, okay? Yes. And this diagonal has, so they correspond to the singular values, okay? Those values actually you can sort them from the largest to the smallest, okay? The large value tells you that you have maximum transmission, a large transmission. Small value tells you that you have a very small transmission, okay? So we have a scattering medium, so the transmission is weak. A priori, you don't have much light going through the system. But if you choose correctly, I mean, if you are able to diagonalize or to decompose the matrix like that, you will find the channels through which you have a maximum transmission through the system. So you can do actually you can do a statistics of the singular values. I'll show you that. Let's keep that. Okay, so if you take a large number of channels, okay, of pixels, what you find is this type of distribution for the singular values, the numbers on the diagonal, okay, and what you find is that you have a lot of channels with very small transmission. So transmission, so that's the number. It's a distribution, okay. So that's the value of the transmission. Transmission 0, transmission 1. Okay, so you have a lot of values for which you have almost no transmission, and I understand why, because it's a scattering medium, so little of the light we go through, most of it will be stopped inside or reflected back. So those are closed, are called the closed channels. Okay, but you have also here another peak here on this side that tells you that you have channels that have almost one transmission 1. Okay. So that means if you are smart enough, you can find a way to sneak through the scattering medium, okay, and have a transmission of 1, although it's a strongly scattering medium. Okay, so those are called the open channels. So there is a way actually to go through a scattering medium by doing this decomposition here. So bimodal distribution of eigenvalues. So that was demonstrated. I don't want to go too much into detail, but the wavefront shaping actually is based on that. Actually, it's based on the fact that you can select the correct channel to maximize the energy at the output. Okay, so that was to finish that chapter. Briefly, I'm almost done with this chapter on imaging. Let me just show you a few another technique here. I mentioned that technique, by the way, the photoacoustic imaging. It's quite interesting and it's quite new. Okay. The idea is to use acoustics and optics to couple the two type of waves. And the idea is that if you launch a pulse, an optical pulse inside the tissues, inside the medium, okay, the light will heat up where you focus the light inside. The light will heat up the tissues, okay, and then by thermoelasticity, you will have a dilatation and a contraction of the tissues where the light is focused, and this effect will create sound waves, acoustic waves, elastic waves actually inside the system that you can detect with the acoustic detectors. Okay, so actually you measure the impact of light inside the medium, how much the light is absorbed inside the medium at some particular position, okay, and you measure it in terms of elastic waves by using transducers, okay. So imagine that if you have a medium which is strongly absorbing, the effect will be strong. If the light is strongly absorbed somewhere, for instance, if hemoglobin absorbs light at some particular wavelength strongly, okay, then you will have a strong effect. You will have a strong thermoelastic effect, and we will measure a high intensity, strong intensity elastic signal, okay. And this way you can actually scan the surface at different levels, and you can image in three dimensions different aspects of the tissue. Not only imaging, you image different components of the tissue, the hemoglobin, the melanin, everything that can absorb the light will be measured. Okay. So this technique is new. It's quite efficient. It has a relatively good resolution and can go quite deep into the tissues. Okay, I don't want to go into details here. And I want to finish with something that we are doing in my lab about imaging. So we try to actually reproduce this type of experiment, but not in optics, with acoustics, with elastic waves. So this plate vibrates, okay, and the vibration is actually emitted by those transducers here. So those small buzzers are like small buzzers that vibrate the plate, okay, and the vibration go through the system, and they are measured on the other side. We measure them optically, so it's very small oscillation of the plate that are detected. And in the middle here we have a scattering medium, okay. So we have a full control here, pixel by pixel. We have a control of the wavefront, okay. So we launch pulses. The pulses can be shifted in time, in phase, in amplitude, okay, pixel by pixel, and we measure on the other side, pixel by pixel, the scattering field. Actually, not only on the line, you can actually scan a full area here to measure the speckle at the output. I show you a simulation of that. Okay, so let's say you start with a laser. With this is like the same for elastic waves. So this is a full simulation actually in 2 dimensions. Okay, so you have a plane wavefront here. And it's interesting to see how the light is scattered. So part of the light is reflected by the medium, and the rest is trying to cross the system. So you see how the intensity decreases across the medium, and you get at the output a speckle. So it's a speckle, okay, because we are in time domain, so the speckle changes also with time, okay. And that's what we are going to measure in the acoustic experiment. So I show you. So I show you what the experiment. So what we have done here is we are going to scan an area here to see the refocusing of light, okay, of elastic wave, sorry, by shaping the wavefront here. So we are going to shape the wavefront so that we will have a refocusing of the beam on the other side of the scattering medium. And here we are in the time domain, okay? So the focusing will be not only in space but also in time. So at a particular position in particular time, we'll have an enhancement of the wave due to constructive interference of all the scattering passes through the system. Okay, so I show you so this is actually an experiment, and this section is a measure at the output of the scattering medium is here. The wave comes here, and you measure. You scan actually an area here, so you see the speckled pattern. As a function of time, the speckled pattern evolves. Okay, and at a particular time, you see refocusing of the wave at a given position that we chose actually. So that's a direct demonstration, and you can see it actually. You can see live the refocusing on the other side of the system. So that's a nice illustration of this technique. So that's what we are doing in the lab. That's the result of focusing. So it's a focusing in space. Okay, you see the spot here, but also in time. So you see that as function of time, the light is you get actually not light, elastic wave is diffusive. Okay, you see the diffusion here, but at some time you get a high peak here, which corresponds to the focusing that particular position. Okay, so that's this what I wanted to show you. So I thank you for this section. We have time maybe to talk a little bit about random lasers. So that would be the ultimate imaging technique. You know, you can see through the cards. You can guess. Okay. So, any question on this chapter? I think it is interesting because you see many examples actually of what we learned during this course, and maybe I take I won't be long. I don't want to go over all these presentations. Just want to show you the main ideas. Okay, random lasers. So before talking about random lasers, let me just tell you the principle of laser in general. What is a conventional laser? Are you familiar with that? Or you got some course on lasers already? No? Not yet? Okay, so the main ingredient for a laser is a gain medium. Okay, a medium where you have amplification, gain, amplification of light, and you have an optical cavity. Okay, here typically 2 mirrors. Okay, so those are the main ingredients for a laser, and the idea is that you have amplification in this medium, light goes back and forth between the 2 mirrors, okay, and you get stimulated emission, and then you cross. If you have enough gain, enough amplification, then gain becomes equal to loss, and you see a very rapid increase of intensity, and that's the lasing action in this system. Okay, so what you need is a gain medium where you have amplification of light, and you need an optical feedback based on this optical cavity. The threshold gain is equal to loss, so that's the condition to get lasing. Okay, enough gain to compensate for the losses due to the fact that those mirrors, they are open. Okay, they let some light coming out. So you need to compensate for these losses. Obviously, if you start to introduce scattering inside the system, okay, that's not good because you are going to increase the losses. Light will come out of the cavity, and it will be detrimental to the lasing threshold. Okay, so it's not a very good idea to put scattering there. although there is a completely different approach that was proposed a long time ago, 1968, by Letokov, who says, okay, let's take a gain medium. Okay, this blue region is gain medium filled with scatterers. Okay, light will be spontaneously emitted by the medium. Okay, and will be scattered by those objects and will exit from the system. The question is, can we get lasing in that condition? So you understand that the losses are huge, okay, because the light escapes from the system. There is no cavity that blocks, that keep the light inside the system. So the feedback with the scattering medium is weak, but because of multiple scattering, the feedback is there. I mean, there is a lot of light coming back and forth inside, okay, that will experience a lot of gain, okay. So if you think about it, you have gain and loss. The objective is to have gain equal to loss. Okay, you see that the loss are proportional. Let's say we have a spherical medium like that. Okay, you see that the losses are proportional to the surface of this sphere. Okay, the gain is proportional to the volume of this sphere. Okay, so if I increase the size of this volume, you can imagine that at some point the gain will overcome the losses, because the losses increase less faster than the gain itself. Okay, the loss increase as r squared, the gain increases as r cubed. Okay, so at some point the gain will overcome the losses, and in that case you'll get lasing. So in principle, Letokov said we should have lasing in his scattering medium, even if we don't have any mirrors. Okay, so multiple scattering, that's the feedback process, and then slight amplification. There is no mirror. Let me skip that. And that was the first demonstration of this effect. Actually, that's something that I demonstrated, but numerically during my thesis. And just a few years after that, it was shown experimentally in this sample. So this sample is made of small particles of zinc oxide. So zinc oxide, again, is white paint. Okay, those particles that are scattering, but they also have some gain. Okay, so this small object here, which is a few micron diameter, was illuminated by a pump. Okay, to excite the atoms. The atoms are excited, so they provide gain. Okay, so at low pumping intensity, you see the spectrum here is almost flat. There is nothing really interesting. So that's the emission as a function of wavelength. So what you see is typically the emission wavelength of the gain medium. And when you reach the threshold, when you reach some value of the pump, increase the pump, at some point what you see is a sharp peak coming out of this noisy background here, and you see under the microscope some intense light which has some kind of random distribution. Okay, then you can increase more the pumping and the gain, and you get two peaks like that, and you start to see some images of modes within this scattering medium, and if you continue, you get more and more modes like that. Okay, so that was the first demonstration of what was called later random lasing. Okay, so this lasing in a random medium, in a scattering medium, without any mirrors, without any boundaries. So it's a completely open system, but because of multiple scattering inside the system, you get enough feedback to reach the threshold and see and observe lasing. Okay, so lasing is observed by these very sharp peaks in the spectrum. So random lasing with resonant feedback. So we have here a feedback which is resonant. So it's phase sensitive. It's a coherent emission. And the question is how this can happen. Okay, it's completely open structure. There is no mirror. There is no cavity. Where is this coherent emission coming from? How is coherent feedback possible in a random structure where phases are randomized? Okay. Okay, that's just advertisement about random lasers. Why they are interesting. Possible application. So this is interesting. If you can make a laser without mirrors, that's very interesting. Okay, because especially in the UV, making good mirrors in the UV is very difficult because you need a very flat and uniform surface of the mirror. So if you can avoid that, that would be interesting. It can be used also as a source emitting from the inside of the body, of a tissue, biological tissue. And it is also used as a very good incoherent light source, especially incoherent light source, which can be interesting if you want to erase the speckle. I will go into details here. So those are different examples of random lasers, different structures that were published. So this is scattering medium filled with some dye, laser dye. You can use also this kind of structure, two-dimensional or one-dimensional actually structure here. I showed you that picture last time. Okay, many examples. That was done in cold atoms actually, random lasing in cold atoms. Okay, so what are the signatures of a random laser? So all characteristics of classical laser, you will have a threshold, narrow emission line, okay, but the spectrum is random. That means you don't know where to expect to have emission in the spectrum. Non-directive laser emission, okay, you don't have this coherent light with the straight beam of a laser. It can emit in all directions, so that's very unusual. Complex structure of the modes. The modes can be quite complex inside the system, and this is strongly dependent on pumping area. So I want to show you that. I want to show you some experiment on that. Let me just say some word about the mode, actually, where the mode coming from. So when you have a scattering medium, if you remember that I show you some simulation of this system here, by playing on the scattering strength of the medium, you can actually excite modes of the system, and the modes can be either extended or they can be confined in this localization. Okay. So when you have localization of light, you can imagine that this is like having a closed cavity. Okay, the scattering medium plays the same role as a closed cavity, and you have a confined mode that should laze when you put gain inside the system. Okay, it's less evident here, less obvious here because the modes are extended. They will leak out of the system, but we'll see that you can get lasing. So that's in the case of Anderson localization, you can guess that lasing should be possible there. And this was done actually first numerically. I show you some simulation here. So what you see, so that's the scattering medium here. Okay, we pump the system, and what we see actually is that the intensity increases and reach some steady state, and the spectrum show a very nice line, very narrow line, and it corresponds to a mode inside the system which is localized, specially localized. So this is the lasing mode, like in the experiment with the small sphere of particles. You see actually a pattern of intensity corresponding to this lasing mode here. So this is confined here inside the system. What's that? Oh, that's for, wait, so that's for a strong contrast too. For weaker contrast, where you have extended mode, you also see lasing, but on an extended structure, okay, which is an extended mode of the system. So that's lasing actually from the scattering medium. So we observe that random lasing can happen in localized regime, but can also occur in the diffusive regime without confinement, special confinement of the mode. The threshold strongly depends on the mode confinement, obviously, and lasing modes are built on the resonances, what are called the quasi-normal modes of the passive system. I don't go too much into details here. Okay, so I show you some experiments. So that's a very nice experiment that we did some time ago. I don't know if you are familiar with optofluidics. You know what is optofluidics, no? So the idea actually is to have a structure where you can flow some liquid, and actually this is used in biology to analyze different types of liquids or whatever, molecules, okay? But optofluidics means that you are using the fluids and lights combined together actually to observe some fluorescence of molecules, some different effects, okay? And we use it actually to make a laser. So the idea is that we have a structure here which is random. So it's not a periodic but a completely random one-dimensional structure, and there is a flow of laser dye, which is the gain medium, through the system, and we close the system. So this time is really unclosed there. So that's an image of the structure. So you have this dye here, which is flowing through the structure here, and the scattering centers, which are randomly distributed inside the structure. You pump the system with light. Okay, so you pump this element here, so you get gain, you get fluorescence if you want, emission of light. Okay, so you pump like that with some green lights. Okay, and what you observe actually is light is emitted by this structure. You can actually see it on the side here, and you can measure the spectrum of this light. And typically that's what you get here. You get sharp peaks in the spectrum, okay? And you see the characteristic of the laser here. Each mode actually starts to laze at the threshold, so this is the measure of the threshold here. And you see this beautiful picture here where you see the emission. Okay. I don't want to tell you too much on that. Okay, so what is interesting is what we call partial pumping. So you can pump the system at different position inside the sample. Okay, let's see what the spectrum should look like. Actually, when you change the position of the pump here, you get a new spectrum. The spectrum, I didn't change it here, but you get a different spectrum as you scan the pump. Like you can see here, for instance. You can pump with different patterns here. Instead of a uniform pattern, you can pump with a periodic structure like that, and you get one spectrum like that. If you pump with a different structure, you get a different spectrum. So the way you pump your system can modify actually the emission spectrum of your system. So that's very interesting. You have some degree of freedom to obtain different signature of your laser. You can do that also in 2 dimensions. That's a 2-dimensional system where you have the flow here going through this system here, the scattering center, which are like cylinders. You pump the system from the top like that, okay, and what you observe is emission around it here. So for different type of pump here, you get different type of emission. Okay, you can actually change the way the system emits. Okay, so from that we got the idea that you can control the emission of a random laser by playing on the profile of the pump. Okay, so the idea is the following. So you have a random structure here, you have gain, okay, and you can pump the system as you want with different intensity. It's the same idea as wavefront shaping, but for gain. Actually, it's a gain shaping if you want. So you can pump differently the system to excite different mode of the system and change the spectrum of your system. So the question was, can we control the emission of the random laser by playing on the profile of the pump? So this is done in the same spirit of the wavefront shaping techniques. You come with a uniform pumping, you get a random spectrum. Okay, can I shape the pump here to get a single mode emission like that? Okay, so that can be done by using a feedback loop. Okay, where you are going to say, I want one mode to be excited and the rest not to be excited. So I show you how we did that. Maybe I should directly the experiment. So we can go for the numerics. That's too much. Okay, so that's the experiment here. You have so this is actually the laser, the pumping laser. The sample is here. You see all these tubes here that bring the liquid, the dye into the sample. The green is the pump, and the orange that you see is the emission of the laser. I thought I had a better image of that. Okay. So how do we do that? So the pump laser here is reflected by, again, a spatial light modulator. So pixel by pixel, we can modify the wavefront of the pump beam, and this is projected on the sample directly. Okay, so you can pump differently the system, and the objective is, starting from a uniform pump, you get a multi-mode spectrum. Okay, so many lines, laser lines, different colors if you want, emitted by the laser. You want to find a way to select, for instance, this peak here, only one wavelength. Okay, so find find the right profile here to select only this peak. So I skip the method here. So you see here, for that peak here, you have an iterative process. Okay, we optimize this peak with respect to the others, and after how many? 228 iteration, you get a very different pump profile that gives you the emission on one particular peak. I show you the experiment live, okay, if it works. So I explain to you. So this is the spectrum here. We want to optimize the green peak here, this one, okay, and the algorithm will choose to maximize this peak and minimize the next peak, the next one, the next highest peak after this one. Okay, so it will minimize the red and maximize the green here. How do you do that? You do that by changing the profile of the pump. So that's the pump here. Okay, here or this different view. So it's either uniform or, so dark means low intensity, white means high intensity, and it's a gray scale. Okay. So by exploring different distribution of pump intensity, we are going to change the spectrum here. Okay. And the system will try to find the right profile to force it to laze on this peak and not the others. Okay, so you see that, you see the iterative process. It's almost okay. So changing the pump here, system changing, the spectrum is changing, and at some point the algorithm will find so you see, sometimes it finds some good configuration, and then it just how do you say, just select that distribution, and it tries to optimize it to reduce the red as much as possible to have a maximum on the green. and this is a measure of the ratio between the green and the red. So that's how you can actually control the emission of the laser. So that's something very interesting, because in a standard laser you don't have control over emission. The emission is fixed by the cavity. Okay. Here we don't have any more a cavity, no more mirrors. Okay, the system is open, but by playing with the pump, actually you can have a tunable laser. You can tune the wavelength of your laser by playing on the pump itself. So you get a new degree of freedom to control the emission of your laser, because the system is open and the modes are not constrained like in the cavity. So that's the main idea. You see, you can actually achieve very nice results. For instance, you have here two modes which are very close to each other. Okay, you can select this one or the other one here with this method. So that's an interesting aspect. So this is due to the fact the system is open. Okay, open means that the modes are not orthogonal with each other. You have new degree of freedom to control the emission. And I just want to finish by showing you what happened in the localized regime. So that's another type of laser, localized laser. So it's so this is actually a polymer. So it's like plastic. Okay. The dimension is about 500 micron length. Okay. And inside this plastic structure, we make grooves like that. So we have an index contrast between the polymer and air, in fact. Okay. So those are the scatterers of the system, and you have a long structure like that with randomly distributed grooves inside the system. The polymer is doped, again, to have gain inside the system, to have amplification. The index contrast is not very strong, okay, but enough you see to see localization. You can show numerically that you have localized states inside the system. I skip that. Okay, so when you pump the system, okay, what you see actually is that, so that's below threshold. Above threshold, you start to see emission, and the emission actually gets out of the sample through the grooves, okay, which are scattering the light. So I don't want to describe that. Then we control the emission here using a special light modulator, and by controlling the pump, we can actually control the emission and select the mode one by one. Okay. And the idea is that from the top of your sample, like here, you can actually image the emission of your laser. Okay. So if you look here, when you select a particular wavelength, okay, for a given distribution of the pump, you observe, as a function of the position, you observe an intensity which is localized spatially inside the sample. For another wavelength, you get another mode localized in a different position, another wavelength, another localized state, more extended than the first one. So actually you excite different modes, localized modes with different extension inside the system. So with this laser, actually we're able to demonstrate localization in this system by looking at the lasing mode, by measuring the mode of the laser, showing the localization. You can show the distribution of the localization light. Okay. I think I will stop here. That's a lot of information, but I wanted really to illustrate the course here with going all the way to localization, okay, and show you that this is a very rich field with a lot of promising direction. It can be imaging, it can be lasing, and there are other new direction. I think the main idea is that scattering is not always a problem. I mean, an obstacle. Okay. Actually, what people try to show is that you can take advantage of the scattering, of the multiple scattering, and you can actually use it to go beyond the limits of optics or waves in general with interaction. it's quite complex in terms of physics. Okay, I try to show you that theoretically it's hard to handle. There are different approaches, but it's not easy. You can have very complex system where you have scattering and gain. You can have also scattering and optical non-linearities. Okay, that's also a new field that is emerging. Actually, this is related to computing. How do you call that? AI is based on the neural networks. Okay, so actually you can mimic a neural networks by multiple scattering in a disordered and non-linear system. So that's really a very new paper that appears recently on that. So actually we are looking for complexity, and out of this complexity you can actually get a lot of advantages, application and perspectives, interesting perspectives. So from now it's now your turn, okay, for starting next week. We try to have like a panel of different topics for different papers. I think that will complete the course. Try to be not too technical, okay? Think about your audience. They don't know the paper, so try to be a tutorial to explain things. Don't put many equations if it's theoretical paper. Okay, we want to understand the physics and try to connect that, if possible, to the course. Okay, to the topics that I try to cover, and I hope it will be fun. So next time I will sit on this side. Okay.
Thank you so much.
Thank you.
Thanks a lot.
Thank you. Wow, it's very exciting. Wow.
At least I try to convey you the excitement.
Hi. מפחיד שהסמסטר עומד להסתיים.
שכן, נראה לי שיכנסו, כאילו, זה דווקא משהו עמק מזה. מפחיד, זה דווקא נחמד, אבל נראה לי ייכנסו לנו יותר בקלות.
אז לדעתי כן.